Okay, so welcome to the next in our videos for Math 1410 Elementary Linear Algebra. This next screencast covers the polar coordinate system, which we're going to be using when we want to convert our complex numbers into polar coordinates. We're going to find that there are a number of calculations that are much easier in the polar coordinate system, in particular when we want to calculate things like powers and roots. Before we get there, we first want to go over the polar coordinates, and I'll also add that if you are rusty on your in your trig, if you need a refresher, I did put together a screencast with a review of trig. It's a little bit on the lengthy side, but it should go over everything that you need to know for that material. Okay. So, how do polar coordinates work? So the polar coordinates are an alternative coordinate system for the Cartesian plane. And that's not a very good x-axis. Let's try again. There we go. So normally we label our axes as x and y, and if we want to locate a point within space, within this plane, right, the way we do it is we measure the distance of this point from both of the axes, right? We measure the distance from the x-axis, the distance from the y-axis. So the coordinates x and y that we ordinarily would use to label a point, x, y, these are often referred to as rectangular coordinates because, well, you can sort of see the rectangle which is formed here. You have x, y, and the origin at opposite corners of this rectangle. You can see the two sides sort of dashed out there in green. And so this is one way of locating a point in space. This is, it's a grid coordinate system. It's a sort of, if you were navigating in, like, I don't know, Manhattan or somewhere like that, you're in a busy city where you've got streets that you can move on. You can only move north, south, or east, west, but those are the only possible motions that you can make. This is the sort of coordinate system that you might want to use. And this, of course, this coordinate system goes all the way back to René Descartes. Legend has it that he discovered this coordinate system while lying sick in bed and watching a fly crawl around on the ceiling and realizing that he could specify the location of the fly by knowing how far away it was from each of the walls. The Cartesian coordinate system, the rectangular coordinate system, it works great for a lot of things, but it's not always the best tool for the job. The other way that you can locate a point in the plane, once you have an origin, right, rather than moving on city streets, think about navigating on the ocean or wide open spaces. If I wanted to get from the origin to that point, I probably wouldn't do it by traveling first horizontally and then vertically. I would probably just go directly from point A to point B by pointing myself in the correct direction and then walking the appropriate distance. And that's exactly what the polar coordinate system is for. So the polar coordinates are calculated as follows. I can construct the line segment from the origin to the point that I'm interested in. I can label that segment by r, where r is the length of that line segment, so the distance from the origin. And we know how to measure distances. We know that r, this distance from the origin, is given simply by x squared plus y squared. And theta, as usual, is just the angle between the positive x-axis and the line segment that you've drawn. So there are a number of ways that you can define that theta, but one way to specify that theta, if you know x and y, if x and y are the quantities that you know, then if you think in terms of, triangle trig, you've got this triangle sitting here like so, and you can think in terms of, opposite over adjacent. You could say that tan theta is equal to y over x. And so your polar coordinates are these two numbers, r and theta, and this simply gives you another way of locating a point in space, right? If I know the value of theta, I know which direction I'm facing. If I know the value of r, I know how far I need to go, and this is going to let me get to the point that I'm interested in. The only thing to kind of beware of here when you're dealing with polar coordinates is note that there are some ambiguities. So, for example, the point. So we might label this point here as, instead of labeling it as x y, we might label it as r theta. Note that the point r theta would be the same thing as the point r, and if I add some multiple of 2 pi, right, where k here is an integer. Um, so so theta is not uniquely defined, because I can go all the way around as many times as I want. I can add as many revolutions as I want. I can instead of going here, I could go once around, but I could go around and around and around and around and around. Um, and I would still end up facing in the same direction. Now probably if you're using this to navigate, you don't want to spin yourself around too many times before you start out, or you'll get dizzy. But as long as you kind of are moving in a straight line in the right direction, then you're going to get to the point that you want to get to. And of course, you could measure, we by default we measure our angles counterclockwise, but you could measure a clockwise angle. That could work too. If you learn about polar coordinates in a calculus course, you may also learn that you can sometimes consider r to be negative. You can consider a negative value, which means instead of going forward while facing in a certain direction, you walk backwards. And so then there are some different ways that you can express a point where you allow r to be less than 0. We're not going to concern ourselves with the case where r is less than 0 in this course, because for us r is always going to be the modulus of a complex number, and we'll see that that's always defined to be positive. In fact, the modulus of a complex number is just given by this quantity here. And the other thing that you should note is that so the origin 0, 0, x is equal to 0, y is equal to 0. It's simply defined by setting r equal to 0. So r is 0, and theta is undefined. There is no value for the angle if you're at the origin, right? If it doesn't matter what direction you're facing. If you're already at the origin, you're at the origin. There's nowhere to go. So the equations that we've written down here, these guys, they tell us how to kind of calculate r and theta if we know x and y. But of course you can convert the other way. A little bit of triangle trig, so cosine theta we know is adjacent over hypotenuse, sine theta opposite over hypotenuse. We can play around, and we can also convert back, and we can say, all right, x over r would be equal to cos theta, so that tells me that x is equal to r cos theta. Y over r should be sine theta, so y is equal to r sine theta. Now, to some extent, maybe this seems like an artifact of drawing my picture in the first quadrant, but you can play around and you can check that if you have a point in another quadrant, you have an angle that lands you in another quadrant. These conversion formulas for converting from polar back into Cartesian, they remain valid no matter what quadrant you happen to be in. Okay, so that's the polar coordinate system. Before we finish with it, let's do a couple of examples just to make sure that we have the hang of it. So let's say we want to convert a few points. So let's convert the points. Let's do 2, minus 2, and let's say 3, 4, 2 to polar. Alright, so let's say we want to convert these 2 points. Let's deal with 2 minus 2 first. Okay, so here we're dealing with, and maybe it helps to draw a little picture. Let's just kind of stick it down here in the corner. So x is equal to 2, y is equal to minus 2, so we're down here in the fourth quadrant, like so. And notice that aside from the sign, the absolute value of x and y, both of them are equal, and so we already know what this angle should be. We can guess the angle, right? This angle is going to be minus pi over 4. That happens to be one of these special angles that we're familiar with, so we can write that one down, and where everyone is happy. We got to figure out what r is. So what is r? Well, we know that r is the square root of x squared plus y squared. So in this case, that's the square root of 2 squared plus minus 2 squared. So that's the square root of 4 plus 4, which is the square root of 8. By the way, you can leave it as square root of 8. If you really feel like you have to, you could write this as 2 times the square root of 2, but square root of 8 is perfectly valid. And so the point 2 minus 2, if we were to write this in polar coordinates, we could write this as root 8 for the r value and minus pi over 4 as the theta value. And again, you're not forced to write that as minus pi over 4. If you want to, you could also do, instead of doing the clockwise revolution, you could go counterclockwise. You could go with, say, 7 pi over 4. That would also be perfectly fine. The r value is set in stone. The theta value, you've got some freedom to choose. All right. What about for the point 3,4? So here is one where, okay, calculating r comes out, this works out nicely. This, our sort of 3, 4, 5 rule, right? 3 squared plus 4 squared. So we get 9 plus 16, which is the square root of 25. So we get 5 for r. Okay, so that's good. Now, when you want to calculate theta, this happens to be a case where there's no nice way to write down the value of theta, right? This point, it doesn't correspond to one of these special angles. If y is equal to 3, x is equal to 4. The best thing we can really say here is that tan theta is equal to 4 over 3. That's about the best that we can do. Or you might say that theta is equal to arctan, if you like, 4 over 3. If you want to work with the inverse, if you're familiar with inverse trig functions, some people write this as tan to the minus 1. You can do it that way if you like. Okay, let me just clean that up. The handwriting wasn't so good there. Now, there will be a few problems where it comes up like this, where I give you a point that doesn't correspond to one of these sort of angles where you can write down the exact value for theta, pi over 4, pi over 3, something like that. Occasionally this will come up, but we'll try to avoid it for the most part and keep the computations simple, especially in a test scenario or something like that. The one place where you may run into this might be on, say, an online homework problem or something like that, where the online homework, often they're generating these values randomly, and you might end up with some funny numbers. The only one thing I'll caution you about is, let's say we did this problem over again, but let's say I gave you this point in the third quadrant. So we were down here. We're at the point minus 3, minus 4. So then you kind of have to play around a little bit, because if you were to calculate tan theta, you would actually get, you would get minus 4 over minus 3, but that comes out to be 4 over 3. And then you run into a little bit of a problem, because it's no longer true that theta is equal to arctan of 4 over 3, because theta is equal to arctan of 4 over 3. That's this angle here, okay? That's this angle that we found originally. This arctan function is defined so that it always gives you an angle in either quadrant 1 or in quadrant 4. It never gives you an angle in quadrant 3. So how do you fix that? Well, one of the ways that you can fix it is you could say, all right, I guess what I'm looking at here is, well, if that angle is theta, then this angle here, that would be the same angle there. So what you would have to do if you wanted to get a point like that, I guess let me draw that a bit better. I'm here, right? Is say that well, this angle is the same as this angle. And so what I'm really looking for, if I want to write down theta, is I'm looking for this angle. And so what I need to do is I need to take this value and I need to add on this half of a revolution. So down here, if I was working in the third quadrant, I would have to say theta is equal to pi plus arctan of 4 over 3. So sometimes, this is where maybe sometimes the trig can get slightly complicated. That's about as bad as it can get, though, for us. Okay. Converting from polar to rectangular. Polar to rectangular is a little bit better. So let's say we do, r is equal to 4, theta is equal to pi over 6. Well, converting this is straightforward because I say, all right, x is equal to r cos theta, y is equal to r sine theta. So now it's a matter of plugging things in. 4 times cos of pi over 6, 4 times sine of pi over 6. So this is 4 times root 3 over 2. This is 4 times 1 over 2. And so my point xy in this case is just going to be the point 2 root 3 and 2. So that's pretty straightforward. The only kind of thing we could make that would be tricky here would be maybe I tell you that r is equal to 3, and again maybe I tell you something like theta is equal to arctan of, I don't know, let's say 2/3, something like that. Okay, so here things are a little bit trickier. If you want to give exact values for x and y, one of the ways that you kind of do this, one of the ways you can figure this out is you draw yourself a little triangle. You put theta in one corner and you say, okay, so arctan 2/3. So this is telling me that tan theta is 2 over 3, right? And remember that tan theta should be like opposite over adjacent. So that should be a 2, that should be a 3. It's a right-angled triangle, so Pythagoras tells me that this should be square root of 2 squared plus 3 squared, so square root of 13. And then I can figure out what cos theta and sine theta should be, because I know I can do adjacent over hypotenuse, I can do opposite over hypotenuse. So x is going to be 3 cos theta, so 3 times 3 over root 13, so 9 over root 13. Y is 3 sine theta, so 3 times 2 over root 13, so that's 6 over root 13. And now you've converted back to rectangular coordinates.